This is Mr. Bob, and in this video I'm going to walk you through the first problem on the conservation of energy practice problems. That's the problem scenario as Rosa drops a 2.5 kilogram rock from a height of 3 meters. It says assume air resistance is negligible in this entire scenario. The first thing we need to do, part A, is to draw a picture, and as you can see over here on the right, that's what I have done. So first point is always to make a clear drawing of the scenario, and it's really important in these types of problems to do that. It can really help you out. The scenario is going to ask you for certain quantities at different heights, and you can see here I've got a height at 3 meters drawn, and then I also show the rock at a point 1 meter from the ground, because later on in the question you can see there are going to be some quantities that we look for there. Now with that in hand, we can proceed with part B. And part B is where we calculate the amount of gravitational potential energy the rock has at the start. Okay, part B. What we're doing here in part B is the following. We are figuring out how much gravitational potential energy the rock has where it starts. To do that, we have to define a reference point for height. And so in this problem, we're going to define it as the ground being the reference point of 0. And that's going to be pretty much the way we do most of these problems. And so proceeding along that vein, what we want to do then is we want to write the equation for gravitational potential energy, and that equals the mass times the acceleration due to gravity times the height. Now when we plug in the values here, the mass is 2.5 kilograms, the acceleration due to gravity is 9.8 meters per second, and the height is 3 meters. So this is a fairly straightforward problem. All we have to do is we just have to multiply these three numbers together. And when you do that on your calculator, you get a value that the gravitational potential energy is 73.5. What are the units on energy? In this case, given the units we're using, we use the standard metric measurement or unit of measure called the joule, and that's abbreviated with capital J. Alright, we're done with part B. Now let's move on to part C. Okay, so part C asks for the kinetic energy at 1 meter, and I'm sure some of you are shaking your head at first because you look at the kinetic energy equation. It requires you to know speed, and I don't give you the speed. So we have to approach this a different way. The key idea here is that air resistance is negligible. That means that only conservative forces are playing a part in the situation. And if only conservative forces, like in this case gravity, are involved, then we know that total mechanical energy is conserved. And so as I've written there at the top of the slide, the total mechanical energy at the 3 meter point for the rock is the same as the total mechanical energy at the 1 meter point. And so what I've done here on the lower right is I've kind of created a data table to help us keep track of these values. So you can see I've got two heights, 3 meters, 1 meter, and I've got the three kinds of energy, the gravitational potential energy and the kinetic energy. And on the right there, the total mechanical energy, as we know, is the sum of the two. So let's see if we can start filling in some values here. We know from our previous work that the height at 3 meters is 73.5 joules. Okay? What's the kinetic energy at 3 meters? Well, the problem says that Rosa drops the rock. So when she's holding the rock, or just as she releases the rock, it really has no speed, the rock initially. So if it has no speed, it has no kinetic energy, so we can put a 0 in for that. And so then if we add these two together, because this plus this, Gp plus Ke equals total mechanical energy, we get a total mechanical energy at the start for the rock of 73.5 joules. And I would normally put in the units, but I'm running out of space there. Okay, what are we going to do at 1 meter then? Well, while we can't figure out the kinetic energy at 1 meter, we can figure out the gravitational potential energy. And all we do for that is we just write Gpe equals mass times the acceleration to gravity times the height. And we're using the same values as last time, although the only thing we're doing differently is we're putting in a height of 1 meter instead of 3 meters. And I'm doing that here on the left, as you see. And when I multiply those values out, I get a total of 24.5 joules of energy. So that value we can put in right here. Okay? So the question is, what is going to be the kinetic energy? Well, if total mechanical energy is conserved, then we know that this value, 73.5 joules, must also be the same as this value here at the 1 meter point. Because after all, that's what conservation of mechanical energy means. The mechanical energy at one point in the problem is the same as the total mechanical energy at the other point. So now that we know the total mechanical energy at point 1 meter above, and the GPE, this is a simple math problem because we know that total mechanical energy equals the gravitational potential energy plus the kinetic energy. And just by substituting those values in quickly, 73.5 equals 24.5 plus the kinetic energy. You can solve this algebraically. I don't have space here, but clearly when you subtract 73.5 from 24.5, you get a value of 49.0 joules, which is your answer. The kinetic energy for part C at 1 meter above is 49.0 joules. All right, on to part D. Now we want to know the speed or the velocity of the rock at the 1 meter point. Well, we know the kinetic energy, and it's equal to 1/2 mv squared. That's the equation we looked at last week. So let's solve that for velocity. Well, if I multiply both sides by 2, I get 2 times the kinetic energy equals the mass times the speed of the object squared. If I divide both sides by mass, I get 2 times the kinetic energy divided by the mass equals the speed squared. And then if I take the square root, I get that the speed of the rock is going to equal the square root of 2 times the kinetic energy divided by the mass. So let's just plug in these values and see what we find. 2 times 49.0 joules, our answer from the last problem, divided by 2.5 kilograms. If you crunch that in your calculator, you come up with an answer of 6.26 meters per second. And that is our answer for part D. You can obviously plug in the numbers first and then solve for V. I find this way that I did it just now to be kind of a more powerful way to do it because then you get to see the relationships between the different variables without plugging the numbers in. There you have part D. Okay, so finally we're at part E, which says find the speed of the rock if it had a mass of 5 kilograms. And you might be tempted just to go back to part D and take your kinetic energy that you already found in part C and divide by mass of 5 instead of mass of 2.5 kilograms. But that would not yield you the right answer. You have to actually kind of go back to the beginning, and I want to kind of show you a sophisticated way to do this. So if we look at the fact that total mechanical energy at that 3 meter point equals total mechanical energy at the 1 meter point, then we can start from there, but we can do it in a way. And so what we can do here is let's just plug it in. Kinetic energy at the 3 meter point plus gravitational potential energy at the 3 meter point equals kinetic energy at the 1 meter point plus gravitational potential energy at the 1 meter point. Well, let's put in the values here. So kinetic energy at the 3 meter point would be, we know, let's erase that. We know that kinetic energy at the 3 meter point is 0 because she dropped the rock, and we've already established that. So 0 plus the gravitational potential energy at the 3 meter point would be the m times the g times the y at the 3 meter point. And this equals the kinetic energy at the 1 meter point, 1/2 m v1 squared, plus the GPE at the 1 meter point, m g y1. Now if we look at something really interesting about this, what we have here is, if you notice, what do we have in each of the terms? We have m. So what we can do here is if we divide both sides of the equation by the mass of the rock, something very interesting happens. What we get is we get a cancellation of the masses in this equation. And what we're left with is something that looks like this. And if we just stop here to look at it, What this is saying is the speed of the object at 1 meter depends on the acceleration due to gravity, the height at which it was dropped, and the height at which it currently is. But it doesn't depend on the mass at all. So just from that point alone, we can conclude that the speed at the 1 meter point is going to be the same answer as it was in part D, which was 6.26 meters per second. Now, if this way, if I lost you here, and if you would just rather kind of go back and start the problem over with a mass of 5 kilograms, go ahead and do that, and you can work through it the same way we did, but you're going to, if you do the work right, you're going to get the same answer, that the speed at the 1 meter point is 6.26 meters per second. Notice this way, the power of kind of keeping the letters, putting the equations in letter form and then working through it in algebra, sometimes terms fall out and it simplifies the problem and saves you some work. Well, that's it. We've done problem 1, and now you can go on and do the other problems, and there is an answer key on Edmodo that I've posted there. Thanks.